Hi, and welcome back to the Thermofluids book club. And this time we're back into fluid mechanics, chapter 3 of undergraduate. But now that we've upped our math prowess, you're going to see how much easier this really becomes. Honestly, we'll bang on kind of chapter 3, and then honestly we'll even get through like 4 through 6 here pretty damn short order because we leveled up our math. Now, still encourage you, dear reader, to go do those problems, right? Solve for the forces and different things like that, and within the problems you get a good idea of what sorts of tools and power you now have in fluid mechanics. But really, the point now is conservation of momentum. And so as we conserve momentum, this is a vector equation. Momentum is a vector. And so we would take a look at the time rate of change of rho and then ui. So remember, I is standing by itself, so this is a vector. That's a velocity field. And then this is d volume. And then the contour integral of rho ui. And this is why it's powerful, because remember that v dot dA that we had before is v dot dA. So again, a sum over 3 on this one. And then this is equal to the sum of forces, if you will, sum of forces. I is the vector. It's got to stay consistent across this equation. Well, the forces we have, we'll certainly have sort of a pressure and a d area, again, in a vector. And you may have some volumetric forces, rho g, and gravity is a vector, and d volume. So this would represent sort of pressure forces and gravity forces. I'm going to save the sort of shear forces later on for a second. Okay, and so in the world of statics, then what you're going to have happen in the world of statics is this will come in and we would set effectively this whole term to 0. That term goes to 0. That term goes to 0. As statics as in the fluid isn't moving. So nothing's changing with time. Nothing is coming across our boundary condition. And we would do the old trick here of converting this. So this becomes 0 on the left-hand side. We convert this into the volumetric integral. So del I of P, and then plus rho gi d volume. And so that's our static equation. And then since this has to be true for everywhere, really you can also naturally see this as our differential equation as well. And so this is pretty easy from a statics point of view, and a lot of times, since gravity is in the z direction, really we would solve this and just say that the change of pressure in the z direction is just equal to minus rho g. So that would be our sort of normal fluid statics problem. And so what this is going to let you solve is, imagine you have some water system and a weird shaped pool deck, and maybe on the pool deck here there's actually, I'll kind of draw it like this, there's actually a window. Well, you can solve this full equation by just integrating on what's the total forces on this, this hatch that's on this weird angle in the pool, right? Because then you could draw your pressure is going to be equal to the water g, and then your sort of height downward, if you will. You can call that c if you like, depending on which direction you like gravity happening. And then honestly, this just becomes an integration problem. So the total force on this is changing this with depth and integrating it out. So those are some of the problems we'll do in hydrostatics. This might be one of the more complicated ones. Right? And we talked a little bit about buoyancy before, and so now we'll just sort of add that. We already had sort of a buoyancy problem. If you have sort of this weird iceberg in water, and buoyancy is keeping it up. Well, actually, you knew now that this is kind of the density of water, g, and the volume submerged. But you can actually go back into this with conservation of angular momentum, honestly, And you could take a look at R cross B. So some center point, and then this is again was the contour integral, and it was rho water G, the depth. That's where we got a pressure from, and then R cross dA. And remember, we're now index notation, so I can actually rewrite that as epsilon I j k R j b k equal to, and then we can turn this into a volumetric integral. And so this is then, it actually becomes dk of rho w g z. There's an epsilon I j k, and sorry, you get an rj in there as well. And so I encourage you to walk through this. What you're going to find, this takes a little bit more math, but what you're going to find is that the force of buoyancy, we actually would notate it going through the center of the volume submerged. And so I'm going to draw a couple really silly diagrams down here, but one would be, here's water, and you have sort of a square-shaped boat, if you will. You're not very, very happy. But here's your center of mass, so gravity's going down, and this might be your center of buoyancy, but found from this equation. And what I want you to see, imagine what's going to happen as you torque this, right? The buoyancy and gravity are doing this, and so this whole system is going to rotate back this direction, and so this is stable configuration. Right? It's stable because the buoyancy is sort of torquing you back upward. Now, in a similar situation, if I had sort of, again, a square-shaped boat, but let's imagine I had a big mass sitting out here. And so maybe my center of gravity is up this direction. So there's gravity, but my buoyancy force is over here, again, in the centroid of the submerged water. And so that's my buoyancy force. Now look at that one. What's going to happen on that one is it's going to keep going. And so this is going to torque in this direction and would be unstable. And so, if you get into ship design or anything like that, you're clearly trying to make things stable versus unstable. When you get into, honestly, like ship hull design, you actually want to have a fairly gentle restoring moment, but if you get all the way over too much, you want a really big restoring moment. Like, nope, that's too much, come back the other way. In fact, aircraft hulls are interesting as well because they actually design it in such a way that it's a pretty slow rocking back and forth, because you have people kind of trying to fly in and go. You can't have this thing sort of bouncing out there irregularly. So it's sort of designed to be sort of the slow meandering restoring force kind of on torque, and then only if that aircraft carrier in like super high seas, when you would have flight, you wouldn't have flight operations, it kind of flares out to make sure that, like, no, you have a really big restoring force if you get too high of an angle. Okay, and so one of the last pieces in fluid statics is you can actually take a look at the atmosphere, and honestly, the temperature versus altitude in the atmosphere does a couple interesting things. And so for the first little while, it gets colder, and then it sort of holds, and then it warms up again. And so, you can honestly get some density relationships with the atmosphere. And so you can kind of come in and say, I have a gas, and I know pressure is equal to rho RT. We'll sort of do as an ideal gas. Okay? And so dP is equal to negative rho G dC. We have that from over here. And so dP over P, you'll get that it is minus G over RT dZ. And so, here's a situation where temperature is constant, so you'll be able to integrate that no problem. But in general, what we have here before on this line is actually T is equal to some T naught minus this lapse rate as you go up in altitude Z. And so when you punch that through, you actually will solve that the natural log of P going to be gravity over that sort of lapse rate, your gas constant, and natural log T naught minus mz over T naught. And so you can get these fairly interesting relations between pressure and this kind of standard atmosphere that you may not find useful. Really, the important part here is we can derive it. It's one of the interesting applications of fluid statics, right? One is sort of this, find the pressure on a hatch. Another one is solve for buoyancy. And then, of course, standard atmosphere stuff works well, but you can also just kind of look up most of the standard atmosphere on the table. You don't necessarily have to sort of use a formula to sort of extrapolate your way out. Standard atmosphere is very tabulated. In fact, you know, like I program a lot in Python, and I can just import the standard atmosphere. And so I really just say, hey, give me an altitude. And I don't have to do this whole calculation on, am I lapsing colder? Am I holding temperature? Am I getting warmer at different altitudes? You just kind of fire it in. And so, you know, this is fluid statics. We'll come back and do a little bit more on sort of the full equations now for conservation of momentum and talk through the different problems that you can solve it. So see you here in a second. Okay, and welcome back. And so I wanted to just finish this episode by sort of writing down all of the pieces that we've now done in its sort of full glory, if you will, in our index notation. And so we have conservation of mass, right, which is the time rate of change of rho d volume plus any amount of density that's being carried across a surface, dAj. And that's equal to 0, unless you're a nuclear engineer. We're not creating or destroying mass. And then momentum, time rate of change. This picks up rho ui, d volume. And then again, there's a ui uj, dAj. And that's equal to, we have our pressure, dAj. And then there'll be sort of our viscous term. I'll go and write it in here since we've talked about viscosity, tau ij, dAj, and then any gravity forces, if you will, rho g sub I d volume. Okay. Again, notice that there's a free I in each one of these. So this is a vector equation. This entire thing is a vector equation because there's I. Anytime I'm having j's, there's a pair of j's, so there's an implied sum over 1 to 3. Implied sum over 1 to 3 over here. Okay, and then we have energy, which we looked at in thermodynamics section. And so that's the time rate of change of rho, and I got to come in here. And I'm going to try and use little energy to represent internal energy. I know a lot of times we use U. I try to reserve U for fluid. And so then you have internal energy plus kinetic energy, which we can now write as uj over 2. So you square up all the velocity components. And then plus gz. And this is in making sure it's in the I direction. Okay, d volume. And then you have the contour integral, and I'm going to go ahead and write in here because we did the math. This is h plus uj over 2 plus gz t, sorry, uj dAj. The reason I did that is because we could take a pressure term and convert it into this, and you get that P plus PV, which is nice, such that the remaining term over here is heat, which we now know to be the integral of TdS. And then this is work, not, this is our regular work, so integral P dV. The work that was sort of on the coming across the control volume got pulled into H over here. Okay, and so that's then our energy. And then we have sort of our second law of thermodynamics, which is we're really just saying that the time rate of change of rho entropy d volume plus any entropy that's being carried across the system has to be greater than or equal to sort of heat over the temperature. So it's sort of entropy has to always be going up. Now, if it's equal to it, it would be reversible, but it otherwise has to be greater than or equal to. And then one that we didn't derive, but you will see derived in your fluid mechanics books, especially in a graduate one, is actually angular momentum. And some of this, the point of delivering, showing angular momentum, is actually come up here. It will show that your stress tensor is symmetric, which is helpful. But the rest of it, again, you can write down here, time rate of change, and this is rho epsilon I j k, and then r j u k d volume, and then contour integral of rho and epsilon I j k r j u k, and this is why index notation is powerful, because I ran out of terms here. This was just sort of r cross v, and so to get sort of the dot product of the velocity carrying things across the area, I now have to say u l d area sub l. And again, we can handle that. This goes back to why index notation would have made this just a mess. Not using index notation to do that. This is going to be equal to, in a shaft work, right? A shaft torque, it would be a vector, right? And then you can have epsilon I j k r j, and then tau k l the area L, and so the stresses that are adding to the torque. So it shows you the power of index notation. I know this might have looked like a lot, but this is actually just a very compact way. And so, as you're going through these problems, chapter 3, chapter 4, chapter 5, chapter 6, I would really encourage you to start here and then cross out the assumptions that don't work, simplify away. Right? Don't be afraid. I've taught this class so many times. I watch students just pick the wrong equation because there's 30 equations, and it's no, there's not 30 equations. This is it. If you're doing a conservation of momentum problem in fluid mechanics, there's one equation. This is it, and you can immediately cross out the terms that don't apply and simplify, and then you can just go either do the integral if you need to, or so many times, especially in undergraduate fluid mechanics. These integrals become so easy because you just say the velocity is constant across this pipe or something like that, and so this integral just becomes this algebra, and then away you go. So keep at with the index notation, be familiar with it, and then go do those problems. Go do all these problems where you're solving for the forces on elbows and constrictions and things like that, and we'll come back here and kind of the rest of sort of fluid mechanics 4 through 6. It's also back in Incompressible chapter 5. We'll actually come back and show a couple interesting derivations from here before returning back into the world of thermodynamics. Okay, we'll see you then. And remember, if you're enjoying book club, like and subscribe.